Hello students, welcome to BTech first year bridge course. In the last lecture, we have discussed the curl of electric field of a point charge and it is Coulomb type field. Now we have seen that if we take the curl of that type of electric field, then it will give us 0. Now you know whenever you have a vector field and if you see the curl of that vector field is 0, it is called irrotational vector. Now what does this mean? Suppose you have a point charge and if it is plus q, then from that plus q charge electric field lines will come out. Means it is diverging in nature. So it is not rotating field. So that's why if we take the curl of that electric field, then it will be 0. Okay. So now if we use the Stokes theorem, then we will get the closed line integration E dot dl will be 0. Now closed line integration of any vector field is also called closed path integration. So closed path integration E dot dl will be 0. Now today we will discuss that and we will see that if the closed line integration E dot dl is 0, that means the electric field is conservative in nature. Now today we will discuss that. So let's consider an arbitrary electric field lines like this, and A is an arbitrary point. Suppose a unit charge, we are moving a unit charge from A to B along this path. So what will be this integration value? That is integration A to B E dot dl. What will be the value of this integration? That we want to find out today. Now let's consider a simple case where it will be easy to find out this integration will be easy to find out. Okay, because this is very arbitrary in nature. The field lines is very much arbitrary in nature. So here this is the plus q charge and from here electric field lines will be diverging, right, and it will be radially outward. So we can consider a spherical Gaussian surface to find out the electric field. We have seen that. So this system has a spherical symmetry. Now in spherical coordinate, if we if we want to find out this dl, then what will be the form of this small length in the spherical coordinate? So in the spherical coordinate, the small length, elemental length can be written like this. Okay, so how can we understand this? So this dr is an small elemental length along r direction. Okay, this r d theta is the length of this small arc, and you can see this the angle is along theta direction. Okay, then r sin theta d phi is along the phi direction, and this is that length. So overall the total length we can write like this. However, here the electric field has spherical symmetry, means the charge is at the center and it is radially outward. So the electric field is dependent on r only. This is independent of theta and phi. Okay, so the direction is along r cap. Now if we do E dot dl, so r cap dot r cap will give us 1. So we will get E, rth component of the electric field, then dr, that means er dr, but all other component will be 0 because r cap here, r cap dot theta cap will be 0, then r cap dot phi cap will be 0. So we will left with this form. Okay, so you know that 1 by r square dr a to b will give us minus 1 by r, then limit ra to rb. Here ra is the distance from here, this ra is the distance of this a point from the q charge. So if we consider the q charge is at the center, this is the length. Okay, now as here the value we are seeing that this value is coming, right? Now you can see that we can reach from A to B through different paths, right? it is not necessary that we have to go along this particular direction. We can go like along this direction, we can go along this direction. So there can be different path possible. But after integration you can see the value we are getting, and that is dependent on the distance of the a point from the origin and distance from the b point from the origin. That means it is independent of the path. So this value, this integral value, is independent of the path, right? So this is very much important consequence of the electric field of this nature. Now if we go back from b to a, then what will happen? The integration value will be like this, right? So that is also path independent. Now if we think it like this, we are going from a to b, that means the point charge we are moving from a to b, and then from b to a means we are again coming back to the a position. Then the circular integration will be 0, because here a to b plus b to a, this integration will give 0, right? This all terms will cancel. So this is the nature of the electric field, that if we take the closed line integration in the electric field, it will give us 0. So that's why it is called the conservative field, right? So path independent nature of the this E dot dl is actually giving rise to this, and this is the actually called the conservativeness of the electric field. Means whatever work done we will do. So if here we are taking unit charge, right? And unit charge into E means what? The force is applied on that unit charge, right? So the work done against that electric force is actually path independent. And if we do the work done in a closed path, that will give us 0. So that's why it is called the conservative field. So if it is not, suppose you have a force and it is not conservative, then if we do this type of integration, means we are moving from a to b and coming back from b to a, then that integration value will not be 0. That means it is path dependent. In which path we are moving, that we have to consider when it is non-conservative. Means there are resistive force in the system. In that case, the force is actually non-conservative in nature. Okay. So today I am ending here. In the next class, we will discuss the relation between the electric field and electric potential, and that will come from this equation itself. That we will discuss in the next class.